Hello and welcome to another video on orbital mechanics. I'm going through the book Orbital Mechanics for Engineering Students and by Howard D. Curtis, 4th edition, and I'm up to problem 2.7. I'm not going to do a video on problem 2.3, 2.4 or 2.5 unless somebody asks, because they're pretty trivial and fairly uninteresting. 2.4 and 2.5 involve using ODE 45 solver, which you can go and do in MATLAB. I might do it later days once I've sorted out my screen sharing and process for that. But for now, I'm just going to do the written examples that I find interesting and throw up the MATLAB scripts as well. So I'm going to start with 2.6 is also quite straightforward, just doing derivatives. So 2.7, it says, starting with equation 2.35a, which is r vector dot v vector equals r derivative. Prove that r derivative equals v dot unit vector r. It doesn't actually say r in the book, but I assume it is there. Wouldn't make any sense otherwise. So it wants to prove that this is true, starting with this. It's quite straightforward, and it also wants to interpret the result. So it's pretty straightforward to get to this. All we have to do is divide by r, right? So and that gives us, divided by r, we get the unit vector r. So r vector divided by r gives us unit vector r dot v equals, and r divided by r is 1, so we get r dot. So that's no problem. And it wants us to interpret the results. So the way I see this is that if you have a vector r and it's going in a direction, say this way, this is our velocity, and let's say so after a period of time, the r vector is now here, right? This unit vector of this dot with the v vector here is going to change at the same rate no matter the length of r. So if you looked at this here as well, if that was the length of r, the angle would still be the same, and you can see it is the same along that line. That would be the same. That would be the same. It doesn't matter the length of r, the unit vector of r is all that matters to get the rate of change, and this angle would change at the same rate regardless. So that's what I take away from that. And move on to 2.8. 2.8 says, show that unit vector r dot product with d by dt, the unit vector r equals 0. So this one's sort of similar as well to the last one. Basically, a unit vector can be broken down into two parts. So we'll just draw that here. So let's say that was our unit vector. This would be the magnitude of unit vector is 1. So this would be theta, and this would be sine theta. So if we do split them out, so we have d by dt cos theta I plus sine theta j. The derivative of that is minus angular velocity minus angular velocity sine theta I plus angular velocity cos theta j. And if we were to put in some values, you would see no matter what values you put in, it changes the direction by 90 degrees. So if we were to put 45 degrees in there, they both give the same number, but this would be negative. So it would go like that, right? 90 degrees. So if the derivative of this is 90 degrees to itself, then itself dot product with the derivative of itself is naught. And that is that. Then 2.9 wants us to show that velocity equals mu over h times square root of 1 plus 2e cos theta plus e squared for any orbit. Now, if you look in the book, it shows that v perpendicular equals, one second, let me just pull that up. Don't want to get them the wrong way around. V perpendicular equals mu over h1 plus e cos theta, and v radially, so inward, is mu h e sine theta, and so the total velocity is v squared equals v perpendicular squared plus v towards the radius squared, not the normal direction. And then if we work that out, which I'll do now, so it becomes basically, you're going to end up with v squared equals u squared over h squared 1 plus e cos theta squared plus mu squared over h squared e squared sine squared theta, and this equals, u squared h squared. Let's take that out now, and we'll say that's 1 plus e squared cos squared theta plus 2 cos theta 2e cos theta plus e squared sine squared theta. Now, cos squared theta plus sine squared theta is 1. So that just, when you extract the e squared, you've got that plus that, and that is 1. That's the identity. So you get u squared over h squared on 1 plus 2e cos theta plus e squared. And then take the square root of that. So drop that, put a square root around it. You have your final answer as required in the book. So that's that. Pretty straightforward. If you have any questions, let me know. If you think I've made a mistake, let me know. And thank you. Bye-bye.